The nature of the business is based around sporting events, so weekends tend to be very busy, which doesn't really clash with your working life. It's a bit unfortunate, but you get caught for let's say Champions League nights, Wednesday evenings, or around the globe if there's a big sporting event like a Super Bowl, which is on in the middle of the night, right? So it's difficult to support this kind of a platform when you have to watch it that closely, when you're worried about load and performance and scalability. So we really had to make bigger changes. We had to come up with something a bit more radical than what was going on here. Now, any group of developers would just, we wanted to build it all again from scratch, right? We wanted to throw it away, we wanted to build it, we knew how we could do it better, right? So that's what we thought, but realistically, business normally isn't going to accept that. So we were very lucky really working with Matchbook in that they're quite technical, and as you may have gathered from Nora's speech earlier as well, they buy into allowing you to innovate or evolve your technology. So they were actually more accepting than we would have anticipated when we went to them with a proposal for a new platform. They felt that they were tired of spending money and resources sort of supporting the platform as it was, dealing with sort of load issues and performance issues, and they weren't getting the opportunity to innovate and develop new features and functionality that they wanted to offer their customers. So they wanted to move past that and still had the ambitions to continue growing as a company. So having got kind of past the initial hurdle and got a bit of buy-in into this concept, we had to start thinking about how would we build a system now that we were getting the go-ahead. So some of the major design considerations for us were obviously the betting transactions, so they're the core of the exchange platform. We also had to think about what I'm calling the market view, which is basically where users get to see the list of markets and the latest prices available for making their trades. We could obviously take into consideration some of the latest best practices, start looking at things like modularization or microservices, continuous integration, all these kind of best practices that have been developed over the past number of years since the initial platform was built. And obviously there's a bit of a reaction to the issues that we're dealing with on the legacy platform. We're kind of wanted to make something that was more supportable, more maintainable, kind of stay away from maybe the proprietary or custom frameworks that cause trouble when you're hiring people or bringing people in, because there isn't a community based around them. There's no foreknowledge. It requires a lot of upskilling every time you hire a developer to work on a platform like that. So we're keen to sort of avoid those kind of problems as well. So just to look a little bit more detail on betting transactions. So betting transactions are interesting in that on a given market, every transaction is dependent on the previous one, or at least can be dependent on the previous one. So if you're trading for a position and the guy before you takes that position, he buys all the liquidity that's available, your transaction can't succeed. So there is a dependency between transactions. And then we have to think about how you handle that dependency, whether we just, let's say for example on the old platform, the database kind of handled that. Through normal transaction, sort of locking and transactions, the database maintained sort of dependency or the relationship between transactions, prevented sort of concurrent modification or any type of concurrent issues. So we had to think about how we wanted to do that. We were pretty keen to try and avoid, locking and that kind of system, because we feel that's just has an impact on performance. But also interesting to consider is the fact that every market is independent. So that allows you to maybe think about other things. So when we were looking at the horizontal scalability aspect and sort of the databases and locking, we were keen to stay away from that. We started thinking about maybe with some of the ideas and concepts that come from event sourcing and Duncan's talk earlier, we started thinking about sort of sequential processing of our betting transactions. And then we were able to achieve, so that allows us to deal with the dependency between transactions, and it also allows us to provide complete fairness to Matchbook's customers, because it's a first in, first out type of approach. And the fact that markets are independent then allows us to actually scale, to partition by market and to scale horizontally across, theoretically as many servers as we have markets. So that's kind of what we were thinking. We were looking at betting transactions. One of the main kind of questions we had to answer is how we were going to persist these transactions. So it is necessary that we persist them. It's necessary so that we can recover our systems if we have a crash or an outage of any kind. It's a regulatory requirement for the industry that we have a record of all transactions. And obviously we want to have them to satisfy any customer queries. We considered traditional relational databases. We've been working with MySQL for a long time, and we kind of maybe were a little bit averse to going down that route again, to have to deal with sort of the performance and scalability issues. We also it's probably a recognised issue with a lot of the traditional databases that they were built on a vertical scaling model, and they maybe didn't handle horizontal scalability and fault tolerance or redundancy, as well as maybe some of the NoSQL databases that had come into being over the recent years. Those guys had sort of been built to address a lot of those issues and had sort of horizontal scalability and redundancy built in from the original architecture from day zero. So we were looking at some of those options that are up there on the screen. We briefly considered as well kind of what Duncan mentioned earlier when he was talking about event sourcing, just using the file system, right? Not using any database and writing directly. We didn't go down that direction because we just felt we wanted to stick to our own business logic, and like I mentioned about proprietary or custom implementations, we kind of wanted to stay away from that a little bit. We also had to consider with file systems is how we deal with fault tolerance across multiple servers. We have to introduce again some notion of kind of a shared storage solution. So we stayed away from that. We actually ended up choosing Apache Cassandra. So Cassandra, if you're not familiar with it, focuses very much on its write path, on insert speed or update speed. It's built around sort of some of the fundamentals that are involved in event sourcing. It's sort of an append system. It's horizontally scalable. It's clustered. You naturally increase your throughput by adding more nodes to your cluster. It partitions data using a sort of a user-defined key, which could be, in our case, let's say a market ID. So its architecture lined up quite well with the architecture that we were trying to build for our betting transactions as well. So we went down that route. So just having a quick look, we sort of put together a dedicated service, a component to handle our betting transactions. We call it the betting engine, or just engine for short. It's loosely a kind of a CEDA architecture, so it's divided into a number of stages. Input is read off the network, is deserialized and added to a queue for processing. The next stage takes the queue, or takes the input off the queue, processes the transaction sequentially, persists to the transaction to Cassandra. That's the result of the transaction or an event in the event sourcing terminology, and then puts the output or the result onto a queue for further processing, where basically the last stage serializes it and writes it back onto the network. So each stage here can apply back pressure to the stage before it if it's getting overworked. So we find that basically the limitation on this is actually the throughput or the performance or the latency of Cassandra. So let's say, like, on average, if you're building a system like this and you think that it takes 1 millisecond to persist the transaction, your throughput is then limited to 1,000 transactions per second if you're processing them sequentially. So we while we were experimenting and working with this, we initially set out to partition our data based on markets, like I mentioned. And we actually found some issues along the way where particular busy markets, again like Super Bowls or World Cup finals, those kind of things, would have a huge number of transactions. And Cassandra actually works better with smaller partitions. So we had to actually go back and revisit our partitioning scheme. Late last year, we introduced a time component where we actually roll over partitions every hour to keep our partitions very small. So this helps with performance on Cassandra. It helps with modifying your cluster if you add a new node or reduce a new node. The data distribution around the cluster is much more even. And so that was something that we learned along the way because we hadn't any prior knowledge with Cassandra while we were doing that. So just to move on to sort of what I haven't mentioned yet is that every betting transaction also includes an account or a wallet transaction. So accounts, every customer has an account, they have a balance, they need to fund their transactions. If they sell something, or if they, after a result of the sporting event, when they win profits from their transactions, they need to get added back into the accounts. Users deposit, users withdraw, traditional sort of wallet or account behavior. So these actually have very similar characteristics to the betting transactions. So on a given account, each transaction has a dependency on the one before it. The amount of funds that are available or the balance that's there. They can be partitioned by account because every account is independent. So we actually ended up designing a component for wallet transactions or for account transactions, almost identical really to the engine, but just partitioning based on an account rather than based on market. So while we had sort of agreed on this is our right pad, we had to really think about our market view. So this is what it looks like on the website. Basically you have a regular sporting event, and you have the sort of the current odds and the liquidity available for people to trade on both sides of this position. So as I mentioned, guys here are looking for every change to see, based on their predictive models, whether they think it's good value or not. So they tend to be making a lot of requests to this. We often see up to 100 times as many requests for the market information as we would betting transactions. So while we were designing a system that we hoped would give us horizontal scalability and performance on the transactional side, we also have to consider the scale that's going to generate on this side of the platform. So we didn't want to reduce the capacity of our betting engine or our wallet service by having them handle query requests as well. And as we started, again, getting into the same kind of design principles that Duncan was talking about, and we started looking at CQRS and how we could handle serving the market requests in a completely different way than through our betting engine and our wallet. So we had picked Cassandra as our database, but Cassandra, as I said, is ideally built for its write performance. It doesn't perform as well on querying or read side, and we didn't want to again go through a situation where we were like with MySQL, where we'd have to have a massive cluster just to support the queries for this kind of a solution. So we started looking at caching as an option again, maybe kind of like Duncan was talking about caching our projections, which would be our prices. We looked at some of the caching technologies that were out there. I mentioned Redis earlier as probably at this stage when we were building this platform being the dominant player in caching solutions. EHCache we were already familiar with from the old platform and our time working on that. And we looked at Hazelcast as well, if anybody's not familiar with it. So EHCache and Hazelcast both are similar in that they're embedded into your application code. EHCache works by storing all the data locally in memory on every node, which is very good for read performance because you've got all the data in local memory. There's no sort of network trips or serialization, deserialization involved. Hazelcast works slightly differently in that it's also embedded, but it partitions the cache data across all the nodes in the cluster. So if you add additional nodes to your application with Hazelcast, you can increase the amount of total data that you can store in your cache. With EHCache, that's not true. So with EHCache as well, every change to the cache has to be replicated to every other application in the cluster. So we found that actually updating the cache became quite expensive for EHCache the more nodes that you add. It's inversely linear or inversely proportional, which is definitely not something you want on a highly transactional system. Hazelcast, like I mentioned, at best gives you the same performance as EHCache if the piece of data you're looking for is local. If it's not local, it's at worst case one remote lookup to either fetch the data on the query side or to update the data on the right side. Redis obviously is a completely external or remote caching solution. So while it is fast, it does mean that you incur a network trip every time you want to look up the cache or update the cache. Redis is quite simple to use, and it's pretty easy, especially when you're dealing with the volume of data that can fit on a single server. Gets a little bit more complicated if you have to start going beyond that. And also Redis doesn't guarantee you that it won't lose some of your cache data during a failure, so we were kind of a little bit worried about that. And we actually started to look at pure in-memory, just plain old Java objects on the Java heap, and how that would perform. And so obviously it gives us the performance of an EHCache when you're reading data, because everything is locally in memory. And then it kind of simplifies our programming approach and maybe reduces a component or a third-party product from our architecture. So it was beginning to look attractive in this manner. We had to start thinking about how we were going to update the in-memory data and keep it up to date based on every transaction. So we definitely decided at the time that eventual consistency was good enough for us. We didn't want to be slowing down or blocking betting transactions by waiting for every kind of cache to be updated before we completed the transaction. So to build an eventual consistency model, we started looking at how to do this asynchronously, and we looked at a few message brokers to implement this. So we picked ActiveMQ as sort of a big open source implementation of the JMS standard. We looked at Kafka as, again, sort of a modern, it's like the NoSQL equivalent to to message brokers, where it's massively horizontally scalable, deals in sort of big data volumes, huge message throughput. But it's also quite immature. And some of the people we had talked to at the time had sort of some bad experiences with Kafka, and they weren't really sure whether it was stable enough or reliable enough for a production system. So RabbitMQ was sort of a third option that we looked at as being an alternative to JMS, being a bit more mature than Kafka. So we did experiments, we did tests with all of them. We found obviously ActiveMQ, it uses the JMS standards based on your queues or topics. It's quite easy to use. It's built into part of Java EE for a long time. But we did find that the performance of ActiveMQ degrades substantially if you want durable messaging, and it's not really. They've added in sort of techniques to handle fault tolerance and more recently, but it's not really. It hasn't been designed in from the beginning. It's a bit hacky. Nobody here ever worked on it. So we looked at Apache, or we were looking at Kafka, and Kafka is very interesting. It's like, again, if you were talking about Cassandra and the architecture we were trying to build, it is horizontally scalable. There's a lot of the same techniques. If you were looking at the event sourcing type of world, I mean, Kafka writes all its messages in a commit log, and allows you to replay messages from any point back in the log. So it is actually suitable for an event sourcing type system. It is quite immature, like we're saying. It comes with a fair bit of overhead if you want to deploy it. You have to operate and manage a Kafka cluster as well as a Zookeeper cluster, because Kafka uses Zookeeper for sort of coordination. We ran a number of tests on it, and we on pretty low-end commodity hardware, we found its performance to be very good. We were getting like well over 200,000 messages a second, published and consumed on just even on a single node. So I mean, and that does scale as you spread your nodes across, or as you spread your messages across numbers of servers. But one of the things that we weren't too enthusiastic about is that in Kafka, it doesn't have a very flexible message routing or filtering capabilities. Basically, it's on the consumer to consume all messages and sort of disregard what it doesn't want. So, or else you have to design your topology where your publisher is aware of your consumers, so it can choose which topics it wants to publish to. And we didn't really want that kind of tight coupling between our services. So we were beginning to lean a bit away from Kafka, and that's kind of where RabbitMQ came in. We found RabbitMQ extremely easy to set up. It does have clustering built in. It's not as horizontally scalable as something like Kafka, but if you do manage your topology across the servers in your cluster, you can gain some horizontal scalability from it. Running the same tests as we did with Kafka, performance was nowhere near as good. We were talking about 20,000 to 25,000 messages per second. Sorry about that. Just trying to find the mouse now. But yeah, so I was saying we were getting about 20 to 25,000 messages per second using RabbitMQ, both published and consumed. We did find it, we think that is certainly enough for what we wanted to do at the time. RabbitMQ does offer great flexibility in terms of, or the AMQP protocol that RabbitMQ implements does offer great flexibility in terms of the ability to route your messages and filter your messages, and it's done with kind of complete, or the publisher has absolutely no awareness. You can just totally fire and forget the messages that you want to publish or that you want to send or broadcast. So that was the way we went for our sort of asynchronous or message communication. So let's say, like putting it all together, we built a kind of what we would call a loosely CQRS system, where our command side or our transactions, the stuff that changes our data, is coming down the left-hand side of the graph here, handled by our engine service or our wallet service, depending on whether it's the betting part of the transaction that takes place on the market, or whether it's an account part of the transaction. And then we persist those transactions to Cassandra, and we also publish the output onto RabbitMQ. And then using RabbitMQ, we're able to hang a number of downstream services off that, where we can filter the events as appropriate at the broker level, so that the actual application doesn't have to do the discarding of the messages that it's not interested in. So we have a separate then dedicated component that consumes all the betting transactions and builds up a projection, as Duncan was calling it, of the prices or of the markets. and we serve all requests for market view information completely from local Java memory. So there's absolutely no remote kind of request, there's no network round trip time involved, there's no serialization or deserialization at all. So that's the approach we went down with that. So obviously building a platform where a company is operating a legacy platform brings up the question of how you're going to migrate the systems. So there's, again, a number of ways we could have gone about doing this migration. We could have gone for a big bang approach where we literally switch over from the old platform to a fully functional new platform. That's obviously incredibly risky. It's a big bang for a reason, but it's incredibly risky because the entire business is now running on your new, not road-tested platform. And if there's a problem with it, it has a far-reaching effect financially for the company, reputationally. It's just high-risk deployment. It's the opposite of what you're trying to do with sort of continuous deployment approaches these days. So another option we were looking at then obviously is the sort of continuous incremental deployment of the platform, sort of replacing pieces of functionality on the old system with the new platform functionality. We're really happy with doing it this way, or confident, let's say, because it would involve a lot of short-term work or development to integrate or connect the two systems together that would really be throwaway once we had kind of finished the full migration. We weren't really keen on it because we didn't want to invest the time in it and the effort in it if there was a way to avoid it. It also introduces its own risk, so that if there is a problem when you roll out a part of the system or feature, if it's in the core of the new platform, or whether the problem is in the integration between the two systems. So a third option that we sort of discussed with Matchbook at the time was that because, again, we're talking about sports here, we could start to migrate individual sports, starting with sort of less popular or low-key sports, entirely from the old platform to the new platform. We could do it completely publicly. So we could let Matchbook's customers know that we're building a new platform, that we're migrating to a new platform, use it as a marketing exercise, for the company to publicize that it's investing in new technology and it's moving forward, sell all the benefits that the new platform is going to bring to its customers. And luckily for us, Matchbook were more interested in taking this approach. And we started to roll this out in sort of mid-2016 with, we actually launched a new sport for Matchbook. So up to that, Matchbook hadn't got horse racing because the old platform couldn't deal with the volumes of trading that horse racing would require. And so we launched a new sport for Matchbook, which was horse racing in beta mode on the platform in mid-2016. And sort of at the time it wasn't, let's say, a fully complete product. There was certain functionality that existed on the legacy platform that wasn't there yet, but it was beta standard, and that's the way we started to sell it to Matchbook's customers. As the year went on, we started to add the additional features and roll them out, and so this was our way of sort of achieving the continuous delivery or the incremental improvements. And then we started to gradually, by autumn 2016, move across the remaining sports, again starting with the less popular, sort of less volume, less financially risky sports. And this way we were really road testing the new platform in production with real users and real transactions. And eventually we got to the point where this spring in February we actually fully migrated all sports across from the old platform to the new platform. So now everything for Matchbook, all betting transactions and all market view requests are being served by this new platform that we built. So just a summary of what I've just been going through. So I suppose after migrating a new platform, obviously the most interesting bit is the results, and bringing us back to the title of this, like what we actually achieved. So sorry, just to mention there that this coincided with a number of other projects that we were doing for Matchbook. As Laura described earlier, there was an evolution of the Matchbook UI. Xanadu also launched new native mobile apps on iOS and Android for Matchbook this year. So Matchbook as a business has seen quite a tech revolution this year. But so just to go back to sort of the results. So Laura gave all these away earlier, right? So there's going to be no surprise on this one. But so we have been seeing up to sort of on an average day, we regularly see over 6 million betting transactions. We peaked the Saturday after Cheltenham with 9.9 million betting transactions. I can't remember, there was a big race on that day, but we peaked at 9.9 million betting transactions. As Laura mentioned earlier, we regularly see about 350 million market view requests every day. And this has been growing now as the new platform has been launching and customers are coming on board with it, and Matchbook is finally sort of starting to achieve its growth potential. And we've actually reached up 430 million requests at the start of this month. So as Laura put some of that in context earlier, she mentioned a couple of sites, particularly the one that we use for the title here was Amazon. So the numbers we got from Amazon were sort of mid 2016. Amazon does have some very big days, obviously, like Black Friday and Amazon Prime Day. But Amazon's averages are reported as being around 3 million orders a day, and their requests are around the 240 million mark on average a day. So it's just to put some context that quite a small team based here in Cork actually ended up building a platform that handles the same numbers of requests as a system like Amazon. And I guess I suppose the reason or why it does that for something that maybe has a tiny fraction of the customers that Amazon has is due to the difference in profile that I mentioned earlier, where users need to see changes immediately, almost in real time, and betting. And as the market's moving, people are coming in and they're trading immediately. It's very different to like a news site or a blog where somebody sits and reads an article before they sort of load the next page, or if the news is updated, it doesn't really matter if you didn't get to see the latest headline. So I suppose the interesting ones for us, so our betting transactions are sort of right pat, which goes all the way through our engine and wallet service and down to Cassandra. With this level of 9 sort of million betting transactions a day, we're still seeing under 20 millisecond average response times. And then the difference, obviously, for our query path or our market view and requests, which are served completely out of local memory, serving up to 420 million a day across actually only 3 instances of this application. We've just got 3 really to give us the sort of fit fault tolerance. We don't actually need 3 to cope with that load, because everything is responding so quickly. The throughput is actually massive. It's way beyond what we would have got with any type of a cache or database backed application. And we're seeing our average response times being well under 1.5 milliseconds. I actually think our 90 percentile response time is about 1.7 or 1.8 milliseconds. So it's been a very sort of successful in terms of the results and what's out there running for Matchbook now. They're incredibly happy with the performance and the scalability they've got so far. It certainly hasn't been seamless. We had problems, like I mentioned earlier, with Cassandra, when we had to start thinking about how to repartition our data, which was a big job. Probably while we're happy with RabbitMQ in terms of the functionality that it provides us, we are aware that that's possibly going to become a performance bottleneck if the system keeps growing. We might have to look at that again in the future. One of the areas that we really did have problems with when we were embarking on this architecture was on the market view side, and getting the right, making sure that the prices were actually correct. We had a number of bugs around this where we were maybe processing events incorrectly, or at one stage maybe not processing them in the right order, and ended up displaying sort of incorrect prices or incorrect market data. And that's been an area that we really had to work on to get this architecture to work very well. So I suppose maybe to echo a bit like what Duncan said earlier, it's a very interesting architecture, and it definitely has huge potential in terms of scalability and performance, but it's probably not something to jump into with your first attempt on a production system. Definitely to sort of experiment with it for some time. And we were very lucky, like I said, with Matchbook, that we were able to launch it in beta mode and publicly as well, so our customers were aware that it was beta mode, that there was a certain amount of allowance for bugs or problems that came up over the first number of months. So I suppose that brings us to the end of that, and I'd like to open it up for if anybody's got any questions.
Yeah, your native app, does that React as well? React native?
No, so our native, I don't cover it, but our native apps have been sort of developed quite separately to our web application or our web UI. Again, maybe some of that is a little bit legacy, going back to what Laura mentioned earlier about sort of the limitations that we had with our UI tech stack at the time. I know some of the guys who work on our web UI are very keen that we would actually merge or converge, and that we would replace the native application development as well completely with our web UI, but it's not there yet. Anyone else?
Is that it? Any other questions? Sean, yeah.
was just interested, because you're storing everything in memory in Java, did you run into any garbage collection problems or anything with Java, given how much it changes?
Yeah, I mean, it's been interesting enough. I mean, as you see from the performance and the response times there, I mean, they're still very, very good. We probably have more work to do in that area. We haven't spent a huge amount of time tuning it. We did have a production issue a few months ago, I think at this stage, where we were running into issues with garbage collection, not due to the volume of data that we were storing in memory, but due to the sheer number of requests that we were serving, that our short-term objects were being kind of churned through so quickly that the garbage collector was coming in so often that it was giving us out of memory errors. They weren't really out of memory, they were just due to the dynamics of the garbage collector. So we made some adjustments on that. I mean, I'm no expert on garbage collection at this stage, I would say, but we're using the G1 collector. We probably can tweak a little bit the parameters on that to give us like slightly better performance. And we do have obviously a guy dedicated to performance testing who's looking into some of that now at this stage, and we will be tuning it further. But like up to this point, we've been getting the platform out to production. Obviously we're happy with that, and I guess like one of the guys in the talk said earlier, if it's not broke, don't fix it. And maybe if we could be into the diminishing returns area when it's working quite well as it is.